Alright, so let's talk a little bit about Chapter 8 here. Talk about some chemical reactions. So as we said, we want to set up a chemical reaction. We have to have something that's at least somewhat unstable, so that if the electrons rearrange in a different way, they can be made more stable, held closer to the nucleus, or in some way, some new attractions are going to form for the charged particles that makes the substance more stable with stronger attraction. To facilitate, though, we need a solution. We usually need a liquid to dissolve everything, so things are moving around. They can collide fairly often and allow the electrons to rearrange. So when you have a chemical equation, that describes what's actually happening and how the electron rearrangement occurs. So usually you might see a full Lewis structure, which is even better than just the formula because it shows you when these two collide exactly how the new arrangement of electrons is different from the original arrangement. In this case, the nitrogen is going to use its lone pair to share with a fourth hydrogen. That creates a formal positive, and the chlorine takes on a formal negative. So in this particular reaction, the rearrangement of the electrons is subtle. It's just that this pair of electrons shared between the hydrogen and the chlorine is just going to stay behind on the chlorine. So the hydrogen is no longer sharing it. So they're not sharing anymore. But now the hydrogen is sharing with this lone pair instead to make that single bond, that extra single bond there. So the rearrangement requires a collision. This thing has to be moving around solution. This has to be moving around solution. They have to collide. When they do, I get this new substance. The new substance has its own identity. It has different properties because the electrons are arranged differently around the atom. Right? We definitely see some big differences here. One big difference is now I have full charges. So that new substance is going to be able to form stronger attractions than the old substance with only the partial charges present on the old substance. So the way to show that is whatever we're starting with, that's usually shown on the left-hand side. That's the reactants. And then the arrow just means that's going to become or be converted into the product that is shown on the right-hand side. And so it's pretty straightforward, nothing really crazy or new there. Often the state of matter is shown in the balanced or in the chemical reaction. That just gives you a sense for what state of matter these substances are in. So if these two come together as a gas, the product would be a solid. So as we said, normally the reactions take place in solution, but gases can also react. They usually react a little slower because in a gas the particles are spread out. They don't collide and meet up very often. But if I had enough moles of each gas and they're colliding fairly often, or even if I don't have a lot of gas but I allow for enough time, those collisions eventually will occur and I'll start to create this new substance with its own specific properties. Sometimes I need a gas to dissolve in a liquid, and once it's dissolved in the liquid then they can collide and I will create a new substance here as well. Right? So anytime the formula is different in the end, or even if the formula could be the same, one molecule could undergo a reaction, rearrange the particles, and they could end up with the same particles all connected in the same molecule, but if they're connected in a different organization, the electrons are arranged differently, it's still a chemical change. So here's another example. Here I've got hydrogen and oxygen. If they collide under the right conditions, the oxygen will start sharing electrons with the hydrogen instead of with itself and make water. So why would this reaction occur? Well, the main reason it occurs is because the oxygen-hydrogen bonds are more stable than the oxygen-oxygen and hydrogen-hydrogen. Because oxygen is more electronegative than hydrogen, the electrons that are shared between the oxygen and the hydrogen, they get pulled nice and close to the oxygen's nucleus. These electrons here can't really do that because both oxygens are fighting over them. And the hydrogen's not very electronegative. It doesn't pull the electrons quite as close to its nucleus. So the electrons are more stable when they're closer to the nucleus. They form stronger attractions with whatever nucleus they have. So in order to rearrange, though, and form these new bonds, I had to start by breaking the old bonds. And that requires a collision. Also, I recognize that I can't create or destroy matter, the law of conservation of matter. So if I start with 2 hydrogens and 2 oxygens, and all of a sudden in the end I only have 1 oxygen, that does not make sense. Where did the other oxygen go? It has to be there. Right? So why not draw it like this? Put both oxygens in there. Maybe this is the product that's produced. Is there any reason why that wouldn't work? Oops. Come on. Right, the whole point of the reaction was to make it more stable. The whole point of the reaction was to give the electrons the ability to arrange in a way that makes them attract as effectively as possible to the nuclei. And this oxygen-oxygen bond isn't as stable. So that's not as likely to stay in that format. So when you have a chemical reaction, if it somehow violates the law of conservation of mass and creates an atom or destroys an atom, that can't be possible. But you don't want to fix it by changing the formula. I don't want to do that, because that would imply H2O2 is forming. To keep the 2 oxygens, I still have to have 2. That would balance it, but it's not what I want to do, because water is a lot more stable than H2O2. And so water will be what's formed. So to fix the law of conservation of mass without changing the formula is what I really need to do. So instead of changing the fact that water is produced, I'll change how many water molecules are produced. And so if I have 2 oxygens and I only want to produce water which only has 1 oxygen in it, I've got to produce 2 waters. If I produce 2 waters, then that's 2 total oxygens. So I put a 2 in front. I don't change the formula. I change the coefficient in front. I'm still forming the more stable substance. I just get a little bit more of it. But now I have 4 total hydrogens. So to keep it balanced, I need 4 hydrogens on the other side. So I need 2 H2 molecules to provide the number of hydrogens I need. So this is called stoichiometry. These numbers out front are called stoichiometric coefficients. And balancing a reaction is creating the stoichiometry for the reaction that we need for it to produce the right substance but not violate the law of conservation of mass. So when you're doing balancing reactions, there's a few hints that you can use to help you. If I just give you a reaction, I tell you to put the coefficients in, the stoichiometry for the reaction. You want to look to see where it's imbalanced and change the coefficients and make it balanced. One trick is to change the coefficients for compounds before changing the coefficients for elements. So if you have a reaction that involves a compound where elements are joined together, and for some of the reactants and products, but other of the reactants or products are just individual elements, try to balance the compounds first. Put coefficients in front of the compounds first. The second one is sometimes helpful, sometimes not, but if you have a polyatomic ion that's sticking together on both sides, so something like this, Na2CO3 reacting with a KCl, maybe you produce a K2CO3 and NaCl, something like that. If you recognize that a group of nonmetals is sticking together and not changing it, that part of the formula, you can kind of treat that as a unit. And instead of making sure you have the carbons balanced on both sides and the oxygens balanced on both sides, you can say, I'm going to balance the number of CO3 units on both sides. So that can be helpful in some circumstances. And then the other key thing is to just be really careful. Keep track of how many atoms of each type you have. As you change a coefficient, think about how that affects each element that's present, and then double check your work in the end to make sure you have equal numbers of each element on both sides. Okay, so let's look at this simulation here where we're balancing reactions. So here's the opposite of the one we just looked at. So water breaking down, right? So in the beginning, if I don't have any coefficients, they're all zeros, I don't have anything happening, right? But this is nice because it gives me a visual. So if I start with one water molecule, that's 2 hydrogens and 1 oxygen. So if the reaction is going to occur, I at least have to form 1 of each product. But it's not balanced, right? Because I've got 1 oxygen here and 2 in the end. I can't just create a new oxygen. So I've got to, if I don't have enough of something on one side, I increase the number on that side until I get more of it. Then I reevaluate. Is it balanced now? Well, the oxygen is, but the hydrogen's not. So if I have more hydrogen over here and less over here, I just bump up the number on this side. Now it's good. So I have a big smiley face there. So maybe I'll look at another quick example. So here I would want to start with 1 of everything and count how many nitrogens, how many hydrogens I have on both sides. So I've got 2 nitrogens here, only 1 on the other side. So I need more of that. So I'll increase that number, bump it up. Now it's balanced. In this case, I've got 6 hydrogens though, and only 2 on the other side. So I bump this up to get more. Still not enough. Bump it up again. There I go. Right, so I just bump each number up by 1 whole digit until they're equal on both sides. One more example here. Start with 1 of everything. So this is a nice simulation because it automatically counts for us how many of each element we're starting with. When you're doing the examples on the exam, you'll have to figure that out yourself, right? So if you look at the formula, I've got 1 carbon and 1 times 4, 4 hydrogens. I've got 1 times 2, 2 oxygens. 1 times 1, 1 carbon. 1 times 2, 2 oxygens. Plus 1 extra oxygen from the water makes a total of 3. And this 1 times 2 gives me 2 hydrogens. And so you multiply the coefficient times the subscript that tells you how many of that atom you have for that substance. So here, carbons are balanced. That's nice. I've got too much hydrogen on the left, so maybe I want to add more hydrogen on the right. The way to do that is to increase the amount of water, because water is the substance that has the hydrogen involved. So I bump that up. Now the hydrogen's balanced, but the oxygen's not balanced. I've got 4 on this side and only 2 over here, so I just put more oxygen on that side, and now I have the right coefficient. So there's a cool game here. You can mess around with that if you want. Most students don't have too much trouble with this, but it never hurts to get a little extra practice. So if you guys want to mess around with that, just follow this link on the slide, and you can get to that little game. So let's look at a couple more examples. So here I've got a combustion of propane. Propane combustion is what people use if they have a gas grill. And when propane collides with oxygen, it can undergo this reaction. It's not dangerous to have propane gas unless you have heat or a spark or a pilot light, right? Why do you need heat to start your grill? You have to press that little button that creates a spark. Why do you need that? What? Right, so we need energy because this has to collide with this with enough force to break up the bonds that are already there. Because I can't form the new bonds in the new arrangement of the electrons unless I break up the old arrangement first. So without that spark, the propane molecules in the gas are moving around relatively slowly. If they collide with oxygen, nothing happens. They have to be moving fast and collide hard in order for the electrons to rearrange. So if I have that happening, then I want to balance it to make sure that I obey the law of conservation of mass. So if I have 3 carbons here and only 1 on the other side, I'll put a 3 in there. So now I've got 3 carbons, 3 carbons. On our hints of ways to make this easier, it said save something that's an element till the end. So since oxygen is not combined with other elements in that particular substance, I'll leave that and put its coefficient in last. So I put this 3 in to balance the carbons. Next I look at the hydrogen. I've got 8 hydrogens over here. Well, I've got 8 here and only 2 here. So I need more hydrogens on the right. So I'll put a coefficient in here of 4 that when multiplied by 2 gives me 8 hydrogens. So now I have 8 hydrogens on both sides. So now to balance the oxygens, I count up all the oxygens on the right. So I put these coefficients in over here. So 3 times 2, 6 oxygens from the CO2. 4 times 1, 4 oxygens there, gives me a total of 10. 10 total oxygens. So I know I need a coefficient here when multiplied by 2 gives me 10 oxygens. So that's why I need to put a 5 in. Got another example here. Here I've got barium hydroxide with a specific formula. It's going to react with HClO4. It's going to produce BaClO4, 2, and water. So in this case, I might want to start by just tallying up what I have of everything. On the left I have 1 barium. 2 times 1 plus 4 more gives me 6 total oxygens. 2 times 1 plus 1 more gives me 3 total hydrogens. And I've got 1 chlorine. On the right, 1 barium. This 2 means I've got 2 of that unit in parentheses. So I would multiply all the subscripts in there by 2. So 2 times 1 gives me 2 chlorine. And 2 times 4 gives me 8 oxygen. But I've also got a water which has 1 more oxygen. So that 8 from that one substance plus 1 more from the water gives me 9. And I've got 2 hydrogen. So looking at what I have, only the barium is balanced to begin with. I've got a minor difference between the chlorines, so that maybe should be easy to fix. So I'll put a 2 here. Once I change the coefficient, I want to reassess the numbers for any element that coefficient is going to affect how many of those I have. So putting a 2 here means I double the number of hydrogens. So I already had 2 in the other substance, so 2 more now gives me 4. Putting a 2 there gives me 2 chlorine. Putting a 2 there gives me 2 times 4, or 8 hydrogens plus 2 more, 10. I'm sorry, oxygens. 8 oxygens plus 2 more gives me 10. So now the chlorine's balanced, the barium's balanced, but the hydrogen and oxygen are not. So since I have more of them on this side, already I want to increase the amount on the other side. So I'll bump this coefficient from what it is, from a 1 up to a 2, and see what effect that has. So now I've got 2 times 2 hydrogens, so that's 4. So that's good, checks out. 2 times 1 is oxygen, so that's 2, plus 2 times 4 is 8, 8 plus 2, now I've got 10 oxygen, so that checks out. So now I've got the correct balanced reaction because I have equal quantities of each element on both sides. Right, notice again, I'm not changing the coefficient here, I'm not messing around with that, the subscript, I'm only changing the coefficient out front that tells me how many of the substances are forming, not what the identities of the substances are. Another example here, I want to do a combustion C5H10. Actually, let's switch this up. Let's go C2H2 and reacting with oxygen to produce CO2 and water. So a combustion reaction is where you have carbon fuel reacting with oxygen to produce CO2 and water. So looking at this one, on the left I've got 2 carbons, 2 hydrogens, 2 oxygens. On the right I've got 1 carbon, 2 hydrogens, and 2 plus 1, 3 oxygens. So maybe I want to start by balancing the carbon. I want to save the oxygen until last because it's an element in one form on one side of the arrow. So maybe I'll put a 2 here. That doubles the number of carbons. And now I've got 5 total oxygens, right? 2 times 2 is 4, plus 1 more gives me 5. The hydrogens are balanced. The only thing that's imbalanced is the oxygen. This is why I balance the oxygen last. Because when the oxygen appears by itself, I can change, once I have everything else balanced, I can change the number of oxygens on that side easily by just adding a coefficient in there, and it will only change the number of oxygen without changing the number of other elements, because the oxygen isn't bonded to any other elements. So what coefficient do I need there to make it equal? mathematically I need 2.5. 2.5 times 2 is going to give me 5. So now it's balanced. Okay? But I can't really have 2.5 oxygen molecules. The oxygen comes as individual molecules, so I'm not going to have half a molecule. So if this happens to you, this is okay. Here's another trick that you can use. If mathematically it required a number 0.5, some number 2.5, 8.5, whatever, something 0.5 to balance it mathematically, then just double all the numbers and it will be balanced with whole numbers, which is what you need. So I have a 1 here, I'll just double it. I'll make it a 2. Double the 2.5, make it a 5. Double the 2, make it a 4. Double this, which is a 1, make it a 2. Now it's balanced. And I can double check if I want. But if it's already balanced and I do this same thing to each coefficient, it should still be balanced. But now I've got whole numbers. So a number that makes more sense when I'm talking about individual units that I can't break down into pieces, I have 5 of those units, not 2.5 of them. Questions about that one? So when chemical reactions occurs, they're often categorized in these ways. So if you combine 2 substances to make one, it's called a combination. I'm not really too concerned about these definitions, just memorizing words. It's not really something that's really that useful. But one substance breaking down into multiple substances is called decomposition. Combustion, you should know, that's when something reacts with oxygen to produce CO2 and water. Very kind of specific reaction, but it's important because we use it to drive. It releases energy, so we use it to drive. You know, if you have a gas-powered home, it heats your home. A combustion reaction is used in your car to push your vehicle forward, assuming you don't have an all-electric vehicle. And so it's a very common reaction. So these terms are probably on the formula sheet. Either way, I don't expect you to memorize them, but you should know what a combustion produces, CO2 and water.